So I titled this called The Wonderful World of Materials because I realized with the other people speaking today, there was a lot of astrophysicists, a lot of people with astronomy backgrounds and stuff like that. And I looked at myself and I said, wait, I'm a little bit, my research is on stuff that's a little bit smaller. So these are just kind of three representative images of some stuff I've done throughout my undergrad. Of just like, nanoparticles I've synthesized in a lab, which is less than 100 nanometers, X-ray diffraction simulations I've had to run, and then microscopy images of really beautiful crystals I have to look at. So just a little bit about me first. Let's see if we can get this PowerPoint working. There we go. I was born in Tashkent, Uzbekistan, which is right here, in case if you don't know where it is, right underneath Kazakhstan, right next to China. My home base is in Fresno, so I'm not too far away. I think you guys are in San Jose. So, and I attended UCLA. I initially came in studying biology, and I intended to have like a pre-med career, to become a doctor and a surgeon or whatever. And I accidentally left with a degree in chemistry and physics. So something happened. I'm not sure what happened. And now I kind of went through the graduation or the grad school process, and I applied the past year, visited a bunch of schools, and I settled on Columbia University. So I'm a entering first year graduate student studying chemical physics at Columbia. This is just a picture that a friend drew of myself and my friends. It's up to you to guess which one is me. Okay, so just a bit of what I did in the past 4 years, because I was kind of making this presentation and just self-reflecting on how far I've come. So as I mentioned, I came in initially as pre-med. I wanted to be an EMT. So I worked as a security guard in nighttime patrol with the UCLA Police Department. That was fun. I tried volunteering at a Ronald Reagan hospital, which is like I think the #1 hospital in California. That part sucked. I didn't really enjoy that. I started a science blog about food chemistry through the Daily Bruin that was mentioned. I did a lot of other stuff. I loved teaching. I got involved with teaching middle school for 3 months. It was a middle school chemistry class. I did so many science demonstrations with liquid nitrogen ice cream, explaining crystallization processes for kids. That was also really fun. And I was also president of a chemistry fraternity, which sounds ridiculous if you think about it, but I mean, it happened. So, okay. I think my journey into science was a little delayed, I have to say. When I did science, I was kind of okay. Like, there was the subject I excelled at, but I was kind of lukewarm towards it. And there was several things that ended up happening in my freshman year that made me realize, yes, this is what I want to do, and I'm at a university, and this is what I want to study. First of all, as I kind of mentioned, these pre-med activities, that's not something I wanted to do. Number 2 was quantum mechanics. Number 3 is I got introduced to the world of material science, which is kind of what I'm going to talk about and kind of what I'm launching myself into, and also quantum mechanics. So there was I would describe this process as almost kind of like listening to music, where when you listen to a song, everything sounds muddled. But then if you listen to it over and over again, and then you listen to it in a different way, you start to hear the different instruments, you start to listen to the time signature, the rhythm, you hear the bass instrument in the background that's hard to hear. That's kind of how my experience was with like my awakening with science, in terms of understanding that there is such a nice structure. Anyways, yeah, so in freshman year, I would stare at this. They showed us this equation in a quantum chemistry class, and I said, why is quantum momentum imaginary? Because I learned momentum was m times v. 4 years later, I understand it a little better. But what really got me interested was in high school, I played around with electronics, and I had to do like the science Olympiad stuff. And they taught me about LEDs, which conduct electricity in one way. But then in a chemistry class, they explained to us that actually it's the chemist who decides to change the material and combine them to really create flow of electrons that go in one way. So this idea of rationally designing new electronic pieces was just so cool to me, especially because I played around with it. And I got obsessed enough to join a research lab early on. So now, when I was in high school, I had no idea what material science was. So it's part of this presentation, I have to give you guys a flavor of what it's about. So material science is essentially the science of stuff, like stuff. I can't explain it in any better way. What you touch, your shirt, your desk, your computer, all that is made up, starting with atomic building blocks that form crystals, that form microstructures on the mesoscale, so around microns. They have really complicated phase separations, really complicated dendritic structure, all this other crazy stuff. And there's so much variety in terms of materials, plastics, metals, semiconductors. And then you get to the millimeter scale, something I can touch. This was, I think, what was so interesting about materials, is because it connected the concepts of chemistry in terms of atoms and reactions, and it translated into something I can interact with in my daily world. I can touch this thing and I can explain why it feels that way using stuff that happens on nanometers, right? I kind of just put this graph out here. Galaxies are way out here, because I'm at a much smaller length scale as things I would look at. So materials, if I can't like speak this up enough. We literally name our historical ages after the material that characterizes that time. We went from the Stone Age to the Bronze Age to the Iron Age. People realized how to mix metals and make stronger metals. We went to steel. Now we're living in the age of silicon, right? Semiconductors and our cell phones and our computers. We're getting launched into what's called the nanomaterials age, where we're able to actually design coherently structures on essentially anywhere from nanometers to microns. And now certain scientists in this community are predicting that we're going to be launched into the control age, which is kind of like a weird thing to say, but it's the age where we actually deliberately control what happens on these tiny processes. Where do electrons go? We can, there's current ideas out there, potentially maybe within 10, 15 years, where we can say, I can literally use light and tell an electron to go this way, or deliberately design energy materials in terms of solar cells and stuff like that. So my presentation talked about perspectives a lot, and I appreciate that, because material science is, they call it a syncretic discipline. It's highly interdisciplinary in terms of that. In order to make progress in terms of the design of materials, you need to have people from all different fields looking at the subject, people from all different aspects of science. And I can't understate this. Material science really is the bedrock of all science. Everybody depends on stuff to build your stuff for experiments. So on one side, you have the chemists, right? This is kind of what my undergrad background was. I like to think of ourselves as nano architects, where you are making stuff, or you're finding new ways to look at it. And looking at things such as with an electron microscope or using X-rays is really a serious bottleneck in terms of how we can advance our knowledge of materials, because you need to develop new tools to look at it. This is a project that I did in my undergrad. I won't be talking about that one just because it's a little too detailed, but literally using X-rays and shooting them at polymers, which is kind of like, you can think of them as little spaghetti. No crystal structure, really much more difficult to predict, but using light scattering to figure out how big are these little crystal structures and whatnot. On the other side of the fundamental chart, you have the physicists who like to look at material science from a more fundamental standpoint in terms of electron conduction. And so this is where I think the exotic physics is. I kind of put that in quotes. You have ideas like superconductors and topological materials. There was a Nobel Prize that was won on topological materials, I think 4 or 5 years ago now, where you have macroscopic quantum behavior. And then on one side, I have this electron traffic. People are really interested in the concept of how does an electron, which is a quantum object, interact with other electrons in a solid and interact with other atoms in a solid? That's a very deep question, and they call it the many body problem, which is because you basically have a mole, an Avogadro's amount of stuff interacting with each other in one way. So just as an example, so maybe you guys heard about the two-body problem, which is Kepler's orbits. If you have two planets, one of them revolves around each other in one way. That problem is exact. You can solve that using Newton's laws. You'll get a definitive answer to predict the future and or read the past, depending on how fast things are going. If you put 3 planets, you can't solve that anymore. You have to put it into a computer to solve it numerically. Now imagine in a solid, you have impossibly complicated interactions. It's 10 to the 23rd, 10 to the 26th. So lots and lots of stuff that interact with each other. It's really fascinating. And I think this is kind of where my interest in chemistry and physics merged really well, because I like to think about really complicated interacting things. And there's really beautiful simplifications that come along and ways we can understand things. There's the mechanical properties of materials. Physicists are important to understand. Why do things, break? Why are things hard? This is mechanics, they call it continuum mechanics. After Newton, came up with his Principia, 100 years later, you had Euler and Fourier and Laplace. They're all studying these mechanics of solids, right? How do you get a bunch of little particles bending and squishing each other? So how do they stress? How do they strain? You have optical properties. You can have crystals that literally change the wavelength of light if you pump it hard enough. Thermal properties. This is a picture of a thermoelectric. So you have temperatures generating electron gradients. And then beyond the fundamentals, you have the engineering aspect of it, which asks questions like, when does stuff break, right? That's a very difficult question, a failure, right? So this is a picture of Aloha Airlines, which is an airplane that would travel around the Hawaiian Islands, right? So and because of that up and down motion, the up and down pressure that kept crushing the entire roof of the airline, just ripped apart one day. So engineers are responsible for understanding that type of failure. Devices, electrical engineers and computer scientists cannot do anything they want without this computer chip, right? These are materials engineers and material scientists and physicists who help build semiconductor circuits. On the other hand, you have biomaterials here. This is the best example I found. It was dental filling, right? So the dental filling that gets injected to fill a cavity in your teeth, that's a materials engineer who says, oh, I have this alloy of mercury and tin that can melt at low temperature, so it's not going to fry my patient. Or now that you combine it with sand, glass, so the glass on your cell phone, Gorilla Glass, how do you design hard glass? How do you design glass that doesn't expand? And then, of course, nanotech. So I don't know if you've gone to Costco recently and you saw these QLED TVs that they have in the front door. Those are using nanomaterials, quantum dots, which is, I have nanocrystals here that's less than 100 nanometers. So imagine a crystal that's about 5 nanometers, that's about 10,000 atoms, right? That's very brightly luminescent based on the size of the particle. I can create TVs with that. I can make biotracers with that, and I can make a lot of really cool stuff. So chemical physics, which is what I'm really interested in, fits right here in the fundamental aspect of things, where I am really interested in the idea of structure and function. It's similar to biology, where cells, you have cilial cells on your small intestine that have hairs, which are designed to move. It's a principle in biology where you have cells that are designed to move, hence they look like that. In the same way, materials function in the very same way. So from my perspective as a chemist, I say, what can I design and what are the physical properties of that? So that's been kind of a lot of what my undergrad research has been about and kind of what I really got interested in and really focused on. So this was done at UCLA through an organization. And just like I mentioned with like how everybody has to work together, there was this organization called TAMS. Don't ask me to read out the entire abbreviation, I don't remember what it stands for. But it's basically centered on magnetic materials. We had engineers, computer scientists, physicists, chemists, all working together as teams of hundreds of people across campuses working together to design nanotech magnets, right? So if you know, for those of you who might have taken physics by now, especially electromagnetism, there's a process of induction. If I have an electric current moving through a wire, I'm going to generate a magnetic field. This is a very common way to generate magnetic fields in material in our life on stuff that's about our size. When you get smaller, the resistance of materials really builds up, and you're going to start melting stuff if you try and generate magnetic fields through induction. Now there was this idea of nanoscale magnets. If I actually, this is the electromechanical response. Depending on the crystal structure of the material, how it's arranged, if I apply an electromagnetic field, you actually literally move the crystal in one way, and that actually changes the magnetic properties. So imagine if you had a refrigerator magnet and you apply an electric field, you can basically turn the magnetization on and off, right? So the guiding principle for this in the chemist's standpoint was, well, we want to be making the new structures, right? So if you look at figure B here, this is what they're doing to design brand new antennas, right? If you look at your phone, the whole size of the phone back here is one big antenna. But that's not really practical because that creates a limit on how small or big you can make your phones, because it has to be similar to the wavelength of light. But you can use electromechanical responses to basically squeeze light down into smaller wavelengths and basically create smaller antennas. So stuff I've done is basically trying to make this M&M structure, which is this is kind of more fundamental science, saying nobody has made this type of thing before. It's a core shell structure. You make a nanoparticle and you try and coat it with another nanoparticle. So you take your piezoelectric or ferroelectric and take your magnet and coat that around it. So that was a lot of chemistry. I'm not going to go into these details here, but just to show you the cool images that I got over time. So You want to make your seed nanoparticles, right? You want to, which resulted in this type of thing using an electron microscope. So it was really great as experience as an undergrad to basically use an electron microscope and learn how to look at stuff that was 20 nanometers. It's just awesome. And here's what's the X-ray diffraction pattern. X-ray diffraction tells you exactly what type of crystal you have. If you look at the list of Nobel Prizes, X-rays consecutively 3 years in a row won Nobel Prizes because the ability to literally look at materials using X-rays, it's basically like an eyeball, right? It's so powerful. And the flexibility of it is just amazing. So more stuff, a lot of organic chemistry had to get involved. This was crystals, but then I had to end up playing with some organic molecules here. Heterocyclically, was that project successful? Almost, but regretfully, I only have this in Snapchat form. But I basically made a ferrofluid. So that is a really strong neodymium magnet, and you can see that I basically made a magnetic fluid, which I thought was so cool. You have the little hairs here. I just think it's great. Hopefully the video is transmitting well enough. So this was really exciting. It was a good way to give up my winter break, I think, during sophomore year. So, okay, moving on. So I did some other stuff in that group, but I had another experience that was really, really formative, I think, in terms of my scientific career, which I got the opportunity to work at Berkeley. This was last summer. And this was done with this organization called Strobe, which is very similar to TAMS in the way that it's engineers, computer scientists, material scientists, physicists, chemists, all working together to design better imaging technology, being able to look at materials better. So I'm not going to go into this too much because I just want to show the cool videos, but spherulites are these little spherical crystal structures that show up all the time in every type of material. They're like little balls or little discs, right? So there was this really interesting OLED material. So if you look at QLED TVs, there's also OLED TVs. So rubrene is this type of molecule that forms a really tight crystal. But then this is a nanometer scale. But then when you look at it under a microscope, it forms these rings. And this was so interesting because how do you get something that forms a nice tight crystal, but then along the way, when you start adding millions and millions and billions of them, how do they coherently form a circle? And why does it look like this under the microscope? What are these sharp lines? So that was a really fascinating question. And that was, yeah, the question was what happens between nano and micro? So the plan was to essentially design what they call in situ, which means you basically look at it live, heating apparatus to just heat it under a microscope and watch it grow. So that was a lot of coding because I did basically design a simulation that, or not simulation, but like a boundary tracking software. This is a water droplet that I applied to the rubrene and basically analyze it, look at average radial growth. So this was a really cool research experience that I got. And these are the videos that I got. I wanted to show it. So this is where you go, ooh, ah. So 10 weeks of work there. Maybe I'll play this one too. And this was a really cool experience just because coming in from a more traditional chemistry standpoint, I worked in a lab where the professor was dual appointed in chemistry and physics. And we got to basically just study self-assembly. How do these things come together? And that was a really cool question. You get to see a lot of cool details when you look at things live. Okay, I think I'm running out of time. So, but I don't know how much more. So I wanted to talk about where I'm going now because I'm a bit younger than I think the other speakers. But because I worked in a chemistry and physics lab, I got to see what they had as the optics table. And this was the cool thing. I don't have a picture of like the actual lab. I just found this online, but they kind of all look like this. I was blown away. I just saw this thing on the table. It was this really complicated arrangement of lenses and all these cool things. And they're doing basically spectroscopy on these molecules, on these materials. So, and this is kind of a whole branch of physics that I had no idea existed until I came to college. So physical chemists have basically revolutionized the way we study the natural world using like really fast lasers that pulse at crazy speeds. And because you can pulse things at crazy speeds, you can excite electrons through quantum mechanical processes and basically watch chemical reactions happening on femtosecond to attosecond scales. If you don't know what femtosecond is, it's 10 to the minus 15 seconds. Attosecond is 10 to the minus 18. For the atto, this is actually a brand new technology that came out like maybe 5 years ago. They use X-rays to look at this. It's almost like an X-ray laser. It's really crazy stuff. But just being able to watch quantum mechanical processes at 10 to the minus 15 femtoseconds, or 10 to the minus 15 seconds, is just astounding. And this technology is being applied towards material science in terms of being able to watch, and I put this in quotes, watch electrons move or charge carriers move through materials. And it helps us understand semiconductor physics and solar cells and design better energy materials a lot better. And which, because there's been serious paradigm shifts in the way we think about materials, right? People used to think, oh, you need to have a totally perfect crystal to have good solar cells. Now people are realizing you can have totally bonkers, defective materials, they call them perovskites, and they're totally functional. They work better than silicon. How do you get something that just looks so busted, but is actually conducting electrons better than a perfect silicon sample would? So this ultra-fast revolution in materials is super exciting for rational design, which is something I'm interested in. And I didn't know how to conclude this. I just wanted to say material science is awesome. Chemical physics is awesome. This is great. I want to show this off. This was something in Berkeley where a materials engineer they basically took transmission electron microscopes and modified them. So they had this like 4-dimensional scanning tunneling electron microscope. And then you think, what the hell is 4D? And then it's actually 2 dimensions in real space, 2 dimensions in reciprocal space. If you want to ask me about reciprocal space, I can talk hours about it. But it's just cool. And I got to just experience this. This is a really crazy machine that requires 3 people to operate, like 3 experts. So we got to look at our samples in that way. It was really cool. So I had my contact info. So that's all for me.